Okay, so the Legendre, this normalization of the Legendre polynomials, how we can normalize if we have two different Legendre polynomials, what is the condition of the normalization? Now we already know the from the orthogonality of the Legendre polynomials that if I have the two Legendre polynomials, the condition for the orthogonality is, that means the Legendre polynomials actually जो है, they are a set of orthogonal functions. You know that this thing we have gone through this thing, that the Legendre polynomials are set of orthogonal functions, set of orthogonal functions on some interval 1 minus 1. You know that wherein we have that integral -1 to +1, some Pn of x or Pl of x, Pm of x into dx. This is equal to 0 for n not equal to m. We have done this part, the orthogonality of the Legendre polynomials. Now, the definition of the Pn, the way we define this Legendre polynomial, or I can say that the Pm, does not guarantee that these that they are normalized. From the definition, we cannot say that whether they are normalized, and in fact, they are not. In fact, they are not normalized from the definition. You know that how we write down the Legendre polynomials Plx, y, and all that. So from the definition of this Pn, we will say that they are not normalized. So how we can this set, or we can establish the condition for the normalization? So we will start with the generating function. Okay, so you know that the generating function for the Legendre polynomial is given by 1 minus 2xh plus h square raised to power minus 1 by 2 is equal to some summation over n running from 0 to infinity h raised to power n, now Pn of x. If I'm considering the definition for the Pnx, the way we define the Legendre polynomial, Legendre function जिसको हम बोलते हैं, we have defined this Legendre polynomial or Legendre function. Okay, now squaring both sides to the above equation, so you will write 1 minus 2xh plus h square raised to power minus 1. When you will square it, it will cancel out. It will be simply summation over n running from 0 to infinity h raised to power n Pn of x whole square. Okay, now what I will do, now I will integrate this particular equation from -1 to +1, and see what I will do. So I will integrate this, integrate the above equation from x is equal to -1 to x is equal to +1. ठीक है, there will be some of the terms जिनको हम cross terms बोलते हैं, they will vanish because of this condition, orthogonality condition, Pnx into Pmx. Anyways, so integrating this particular equation, I will write down this equation as -1 to +1. I will write down this as 1 divided by 1 minus 2xh plus h square, okay, into dx will be equal to some summation n running from 0 to infinity. Now h raised to power n, h square, so it will be h raised to power 2n. Okay, now integral will be to this function -1 to +1 Pn of x whole square into dx. You can name this as equation 1. Okay, now see what I will do in the left hand side. I will say that let 1 minus 2xh plus h square will be equal to y. Okay, now on differentiating with respect to x, what I will get, so this will be, or I can say that this dy will be equal to simply -2h, right? So then what will this particular equation become? Okay, so this particular equation, now the limits will also change. See, when y is equal to -1, when x is equal to -1, it will become y क्या हो जाएगा आपका, यहाँ पे लिमिट्स आप देख लीजिएगा. So when x is equal to -1, it will be 1 plus h 2h plus h square. So, or I can say that it will be 1 plus h square. And when x is equal to, this is -1, when x is equal to +1, it will be 1 minus 2h plus h square whole square, h square. So it will be 1 minus h whole square, a minus b whole square. Okay, so the limits will also change here. So then I will write down this equation as I will write down this equation as this particular equation जो मैंने यहाँ पे left hand side of this particular equation, only left hand side part. So I will say that this integral minus 1 to plus 1 divided by 1 minus 2xh plus h square into dx will now be equal to, okay, now see, कहाँ गया ये, okay, 1 minus 2xh divided by h square. So I have just substitute this will be equal to y. Okay, what is dx? This is 2y into dx. Okay, so 2y into dy, okay, and into dx. So the dx will be dy by 2h. So I will write down here this as 1 by 2h integral. Now lower limit will now become 1 minus h square, 1 minus h square. I am changing the limits. Actual में ये आपका 1 minus 2h हो जाएगा. Then changing the limits, it will change it to plus 1 minus h square, 1 minus h whole square rather, and 1 plus h whole square. राइट, यहाँ पे जो है ये माइनस साइन है, बट यहाँ पे जो लिमिट्स आपके आएंगी दैट विल बी 1 प्लस एच टू 1 माइनस एच. जब मैं इनको रिवर्स करूंगा द साइन ऑफ द इंटीग्रल विल चेंज. सो दैट्स व्हाई आई एम राइटिंग इट दिस एज ए प्लस 2h. अदरवाइज ये माइनस 2h into dx यहाँ पे है dy. ओके, देन इट विल बी dy by y, राइट, dy by y again. Okay, so now I can write down this integral as it will be now dy by y. It is ln of y, ln of y. So I can write down this as, the 2 will cancel with this square term. I will just simply write this as it will be 1 by h ln of, okay, when you are going to apply the limits, it will be 1 plus h divided by 1 minus h, the value of this whole integral, because यहाँ पे integral it will be ln of y plus some constant, उसमें मैं interested नहीं. Now substitute the value of y, so it will be ln of 1 plus h square. समझ रहे हो बात को? Shall I, इसको मैं यहाँ पे पहले लिख रहा हूँ. जब आप इसको इंटीग्रल करोगे it will be ln of y, so it will be simply ln of y from the limits 1 minus h square whole square and 1 plus h whole square. Okay, now so it will be ln of 1 plus h whole square divided by ln of 1 minus ln of 1 minus h whole square. So this will be ln of 1 plus h whole square divided by 1 minus h whole square, or I can say that this will be twice. So this will be twice ln of 1 plus h divided by 2 divided by ln of 1 plus h divided by 1 minus h. Now this 2 and 2 will get cancelled out, this 2 will get cancelled out, and I will get 1 by h ln of 1 plus h divided by h. Is it okay? Okay, so the value of this particular, okay, so if you understood it, okay, so the value of this particular integral is 1 by h, 1 plus h by this, but we have the from the equation 1. Now before that I will just expand it in the powers of, in the power series. You know that how we expand this ln of 1 plus h and 1 minus h. Ln of x, it's like ln of x, it is always given by 1 plus x plus x plus, let me show you. Okay, I will just write it on the next series. The power series of ln of x. What is the power series of ln of x? ln of x का power series क्या है? 1 plus x square by 2 factorial plus x cube plus x 4 x 5 so on. So here x is 1 plus h divided by 1 minus h, right? So when you are going to expand it, 1 plus h, this thing, okay, now expanding in power series, that is 1 by h into ln of 1 plus h divided by 1 minus h. So जब आप इसको power series में expand करोगे, you can write down this as twice summation sub n running from 0 to infinity h raised to power 2n divided by, okay, can you hear me? Can you hear me?
जी सर।
Yes, sir.
Okay, there was some issue with the internet. Okay, so what I was saying, I have to start from that very point. It's raining very fast. Okay, so I was saying when you will expand this 1 by h into ln of 1 plus h divided by 1 minus h, you will get the expansion will be like twice summation n running from 0 to infinity h raised to power 2n divided by 2n plus 1. So this I am giving you as a little assignment. 1 minute का काम है, इसको expand करिएगा. 1 plus h, you can also expand it like 1 by h, 1 plus h and minus ln minus 1 minus h. You know that what is the expansion of, there are too many ways. Either you can treat this as whole x as a function, as an argument, or you can also take this as ln of 1 plus h, ln of 1 plus h minus ln of 1 minus 1 minus h, right? So ln of 1 plus x, you know that what is the expansion? Its expansion is like x minus x square by 2 factorial, x square by 2 plus x cube by 3 minus x4 by 4, so on. Or you can say in the summation, it is summation n running from some 0 to, not 0, summation 1 running from 1 to infinity, okay, minus 1 raised to power n minus 1 and x raised to power n divided by n. Similarly, you can apply the same, just add up the two terms, you will arrive at this thing. So this, just try to solve it yourself. Okay, so now अभी जो मैंने इक्वेशन फर्स्ट जहां पे आपसे कहा था उसको इक्वेशन फर्स्ट कहा था. So then that particular equation, I will rewrite that equation. ये equation integral minus 1 to 1 dx divided by 1 minus 2x h plus h square is equal to summation over n running from 0 to infinity h raised to power 2n, okay, integral minus 1 to 1 pnx whole square into dx, pnx whole square into dx, right? Okay, so here I will just equate the coefficient of equation from this equation, name this as equation 2, powers of h raised power 2n. यहाँ पे भी h raised power 2n है, वहाँ पे भी h raised power 2n आपका है. So on equating from these two equations, on equating the coefficient, the coefficient of powers of h raised power n, or I can say the coefficient of h raised power 2n, right? So we have this integral minus 1 to 1 pn of x whole square into dx will be equal to, okay, so what is the coefficient here? Coefficient of this, it is simply 2 by 2n plus 1, 2n divided by 2n plus 1, right? The coefficient of h raised power 2n is 2 divided by 2n plus 1. So on equating these two equations, this was equation first, this is as equation 2. So I am equating the coefficient of h raised power 2 on both sides. You will get that this value of this integral is equal to 2 divided by 2n plus 1. Okay. Also, as I said, the orthogonal functions, जो orthogonal functions हैं, since also integral minus 1 to 1 pn of x into pm of x into dx is equal to 0 for m not equal to n. Equation जो मैंने शुरू में पहली equation लिखी थी, orthogonality condition. Now combining these two equations, I can just combine these two equations. So on combining these two equations, I will say that the integral minus 1 to 1 pn of x, okay, pm of x into dx will be equal to 2 divided by 2n plus 1 delta mn, Dirac delta function. See what I mean? So this is what we mean by the normalization condition. So if m is not equal, if m is not equal to n, you know that this delta mn जो है, delta mn, this is equal to 0 for m not equal to n, and this is equal to 1 for m equal to n. Okay, let us go to this particular equation now, this equation, where m is not equal to 0. When m is not equal to 0, so this will be 0. So this will be pm pn. Okay, so when m is not equal to n, when m is not equal to equal to n, this is 0. Okay, then this we will get this equation. If m is not equal to n, so this will be pnx, pmx will be equal to 0. Now, if m is equal to n, if m is equal to n, then pmn, pmn, it will be pnx whole square, because this will be the same as this. We can take this as a square, and this is equal to 1, so it will be 2 divided by 2n plus 1. So this will be the 2n plus 1. So these two separate equations for different values of m and n, I can just combine, and this is what we call as a, this is a normalizing factor. This is known as a normalizing factor. जैसे आप कोई वेव फंक्शन होती है, तो नॉर्मलाइजेशन ऑफ अ वेव फंक्शन साई स्टार साई, आप कहते हैं दिस इज सम इक्वल दिस इज इक्वल टू सम n स्क्वायर लेते हैं ना, और यू कैन से दैट द मॉड ऑफ साई स्क्वायर इज इक्वल टू mod of psi square is equal to n square. Psi square x is called normalization condition. When we are normalizing the wave function, then you say that this n inverse of some function psi, this is known as, this condition is known as the normalization, and this is known as the normalizing factor. So simply here, this 2 divided by 2n plus 1, this is what we call as a normalizing factor. So this is the way we actually have the normalization condition for the Legendre polynomials. Okay, so orthogonality as well as I can have um, orthogonal condition as well as the normalization condition. I just combine them in one single equation, and that particular equation is this. So corresponding to two different values of whether m is equal to n, this will be this particular equation, and for the m not equal to n, we will get 2 divided by 2n plus 1. Okay, so this was some little concept about the normalization. Actually, we were supposed to do with the where we did the orthogonality condition, but at that time we were not knowing the this generating function. वहां पे हमें generating function तब तक नहीं पड़ी थी, so that's why I didn't touch it here. Now just go to that particular, वहां पे हमने ये condition पहले prove की हुई है. Go to that orthogonal condition, just go to that lecture. We have proved this lecture. Now this is actually an extension to that particular. It is in connection with that. It is actually one and the same lecture. Okay, it's the same lecture, but I just didn't touch it here because we were not knowing the generating function at that time. Okay, now I will give you some an idea about, if you have any questions you can ask regarding this, so that I will move to the next thing. I'm not going to take your much time, just only one lecture in uh, but if you have anything to ask regarding this question, this normalization, or you do not understand any of the point, I did it everything except I ask you to expand that in the powers of h, expand the ln of 1 plus x. Okay, now I'm just going to give you an idea about this associated Legendre function, associated Legendre functions. Associated Legendre function, what actually are associated, because they also arise in many physical problems. So this is just an Legendre functions, but because of some some factor, we called this as an associated, some extra factor, we call this as an associated Legendre function, and it arises in the physical problems because of certain things which are there. So that I'm going to tell you in a while, but फिलहाल, so the associated Legendre function, जैसे आपके Legendre, when you say the Legendre differential equation, you know that is 1 minus x square y double prime minus 2xy plus some L into L plus 1 into y, this is equal to 0. Okay, so this is Legendre function. So what is there in the associated Legendre function? The associated Legendre function actually takes the form as, it's same as this, but except one extra factor, 1 minus 2xy prime, okay, plus some L into L plus 1 minus m square divided by 1 minus x square, okay, into y, this is equal to 0. Because of this extra factor, this becomes different from this general Legendre differential equation. Okay, so this actually Legendre associated Legendre equation has the form like this. Okay, and the solution to this particular equation is like, equation is like 1, we will just try to obtain it, the solution also, 1 y is equal to 1 minus x raised to power m by 2 dm u by dxm. So this function is what we call as a Legendre associative Legendre function. Associative. This is a solution associative Legendre function. Okay, associative Legendre. Now we will try to find out this how whether this is solution to this differential equation or not. Actually, which is very simple and very easy. We do not need to go that जैसे हम उसमें power series solution से find करते हैं solution. So what I will do, I will just use the Leibniz theorem to find out the solution. Take the nth derivative of this particular differential equation. Okay, fine. So okay, now in this equation, for this particular equation for m equal to 0, this will be simply the Legendre differential equation. So this will be the simply the for a special case of this is called as a we will arrive at a Legendre differential equation. Okay, now why does, before going to find out the solution, how we find out the solution, the जहां पे हम जहां जहां पे मैंने इंपॉर्टेंस ऑफ द लीजेंडर differential equations आपसे कहा था कि how do does it arise where we have this spherical coordinates जहां पे मैंने आपसे कहा था when we this actually expand this Helmholtz equation or the Laplace equation in the spherical polar coordinates, and we arrive at the equation, the one of the equation that is what we call as a Legendre equation. To find out the solution to such problems, we will have we need to solve this Legendre differential equation. Okay. Okay, fine. So see how I can find out the proof in just a few steps. Now the Legendre equation for u, I can write down the Legendre differential equation for u. How I can write that? 1 minus x square u double prime minus 2x u prime plus L into L plus 1 into u is equal to 0. So this is a Legendre differential. This is a Legendre differential equation for y, and this is a differential equation for u. Now what I will do, I will just differentiate this particular equation, differentiate this equation m times using this Leibniz theorem. Leibniz theorem. So when we are going to differentiate it n times using Leibniz theorem, so what could be the solution? So the solution will be like, I will write down the equation, then I will see how I write it. 1 minus x square v double prime minus 2x v prime plus L minus m. So this is when you are going to differentiate it with this one when m times L minus m, L plus m plus 1 into v is equal to 0. Now you will say, where does it u come from? Huh? This u is nothing. When you are going to differentiate this m times, this v is simply dm u by dxm. When you are going to differentiate this u with respect to m, with respect to x, m times, so instead of this I will write simply 1 minus x squared this minus 2x v prime L minus m, L plus m plus into this is what we get from the Leibniz theorem, taking the derivative m times. Okay, we have used it earlier in some problems. I do not remember actually where does we use it. Leibniz theorem जहाँ पे हम taking the nth derivative. Okay, now what I will do, I will just set this y equal to, now set this y equal to, that is y of x, set this y of x equal to 1 minus x square raised to power m by 2 v of x. I'm just substituting instead of y, I'm substitute this 1 minus x square raised to power m by 2. Okay, so or I can say that this v of x is equal to y of x into 1 minus x square raised to power minus m by 2. Now on differentiating this differentiating v with respect to x. So what I will get, so this v prime, when I am going to, so v prime will be equal to, okay, this 1 minus x square raised to power minus m by 2, I will write it as such. Then y of x, it will be now y prime plus, when you are going to differentiate it, minus m by 2, एक में आपका y prime हो जाएगा, this is a constant, so this term will remain as such, plus now I will write down this y as such and taking the differentiation of this term, so it will be plus, this will be m x, right, by 1 minus x square, because this minus 1 x square into y. समझ रहे हो बात को? यहाँ पे मैं इसको डिफरेंशिएट कर रहा हूँ, एक में आपका 1 माइनस एक्स स्क्वायर कॉमन रख रहा हूँ, इसका डिफरेंशिएशन y प्राइम आ जाएगा. नाउ अब दूसरे में आपका y और x रेज़ पावर माइनस m by 2 में कॉमन फैक्टर यहाँ दोनों में आ जाएगा. सो दूसरे में अब क्या कर रहा हूँ मैं, अब यहाँ पे मैं इसको कांस्टेंट रख रहा हूँ, ओके, द y को मैं ऐसे ही रख रहा हूँ और इसका कांस्टेंट कर रहा हूँ, बिकॉज़ इट्स इंटीग्रेशन विल बी 1 माइनस एक्स स्क्वायर रेज़ पावर m by 2 minus 1, है कि नहीं? आई विल इलैबोरेट वन, और दूसरा जो है डबल प्राइम आप करोगे. सी व्हाट आई, पहले मैं इसको इलैबोरेट, आई विल जस्ट इलैबोरेट इन लेट. इट इज y of x, yeah, let me suppose it is 1 minus x square raised to power minus m by 2. I am keeping it as such, and then y prime, okay, plus then uh, taking the differentiation of this, it will be 1 minus x square raised to power minus m by 2 minus 1, okay, but यहाँ पे आपका minus m by 2 भी आएगा, this is equal, okay, minus m by 2 plus minus m by 2 1 minus x square raised to power minus m by 2 minus 1 into 2x into y, because this is minus 2x into y into minus 2x into y, इसका इंटीग्रेशन जो है. नाउ बट ये माइनस यहाँ पे है. नाउ आई एम गोइंग टू टेक 1 माइनस एक्स स्क्वायर रेज्ड पावर माइनस m by 2 अगर मैं बाहर ले लेता हूँ, ओके, सो यहाँ पे आपका क्या रह जाएगा, y स्क्वायर, दिस माइनस एंड माइनस विल मेक इट प्लस, दिस 2 and 2 will go, okay, this minus and minus will become plus, this will be mx, यहाँ पे मैंने रेज पावर माइनस m by 2 बाहर लिया है, so it will be minus 1, so it will simply mx divided by 1 minus x square, okay, mx divided by 1 minus square into y. So वही मैंने यहाँ पे लिखा है 1 minus x square into y, taking the differentiation. Now similarly, now you need to go the second derivative. So now v double prime from this equation, v double prime, this will be equal to 1 minus x square raised power minus m by 2. इसी तरह से now we have the three different terms. एक आपकी ये जाएगी, so यहाँ पे एक y double prime आ जाएगा, so यहाँ पे जब आप इन दोनों terms को आ जाओगे, यहाँ पे एक constant रह जाएगा और ये y double prime आ जाएगा. Then we have a this term mx and this term, so we will have four different terms. This is what I am giving you an assignment. इसको जरा खोल के रखिए, मैं यहाँ पे directly लिखूंगा ये, लेकिन you just elaborate it जैसे मैंने इस वाले को first को elaborate किया है. Okay, so this is y double prime plus 2mx, because यहाँ पे mx divided by 1 minus x square एक बार फिर से आ जाएगा, 1 minus x square into y prime plus m divided by 1 minus x square into y prime plus m into m plus 2 divided by 1 minus x square raised to power 2 x square into y. Okay, so ये जो है you need to this is giving you an assignment. इसको जरा पहले इसको दो टर्म्स में लिख लीजिएगा. You just write this as 1 minus x square raised to power minus m by 2 into y plus 1 minus x square raised to power x square raised to power minus m by 2 into mx divided by 1 minus x square y prime. पहले इसका डिफरेंशिएशन आप करोगे, इसका हमने ऑलरेडी कर ही चुके हैं वैसे, y into 1 minus, इसका ऑलरेडी ये आ जाएगा. Then we need to have the differentiation of this term. इसका डिफरेंशिएट करके दोनों को ऐड करके you will get all these terms. Okay, so now when we are going to substitute all this v and v prime in the equation जो हमने अभी फाइंड की थी, this very equation जो equation for v लिखी थी, this equation, so we will have, so substituting this equation in this particular sorry, in this v and v double prime in that equation, you will get a Legendre differential equation. You will get a Legendre differential equation. So the Legendre differential equation, that is what we have, 1 minus x square y double prime minus 2x y prime plus some L into L plus 1 minus M square divided by 1 minus X square into Y is equal to 0. On substituting these equations in that equation जो अभी इससे पहले हमने लिखी है, so thus this so it will satisfy this Legendre differential equation and we will say that this y actually is s, यानी y जो मैंने यहाँ पे लिखा था, जो मैंने suppose किया था, so y, that is y is equal to 1 minus x square raised to power m by 2 into v of x. शुरू में मैंने v of x के बदले लिखा था y is equal to 1 minus x square m by 2, this is dmu by dxm, because मैंने vx कहा आपसे अभी कि vx is equal to dmu by dxm. So either you can write it like this or you can write it like this, but you should be able to know what actually this is. So then I will say that this y is equal to this जो मैंने यहाँ पे ये लिखा था, this is a solution to a Legendre differential equation because it satisfies the Legendre differential equation. And sometimes also we represent it by PLMX, and we say that this is 1 minus x square, right, m by 2, and then dmu by dxm. We do not call this as a Legendre function, we call this as an associated Legendre polynomial, associated Legendre polynomial. And these associated Legendre polynomials are also of very great importance in the physics. Is it okay? So now all you need to do is to find out the rest of the things I have done. So you have this equation before you. You just follow these steps. The first part is what I have. This I have already obtained. Only thing is we were having only the y prime 1 minus x square. This is y prime here. Huh? This is y prime, and then the second term is like this v prime y prime. This is not y prime. Y prime is k. This is simply y. Is it okay? Okay, so with that we are done with this Legendre kind of a thing, Legendre differential equation, associative Legendre reconciliations, orthogonality, and the normalization, genetic functions, and some other things. So now we are left with two other equations. One is called as a Harmonic differential equation, and the other is called the this Legio's differential equation. And I cannot do this today because it is actually very lengthy topic. It will take almost 1 hour. Now you have a minute or so. If you have to ask something, you can quickly.